What I'd like to do in this video is just run some sample problems now that you've seen some of the rules of bonding and how covalent bonds work and you understand that. So if we just have something, right, a molecule that's made out of, say, carbon, which has 4 bonds, oxygen, 2 bonds, and hydrogen, 1 bond, you're not always given the structure of a molecule when you're given chemistry problems. Sometimes you're given something that just kind of looks a little bit like this, right? You might get... Okay, so what this is indicating is that we have 1 carbon atom, 4 hydrogen atoms, and 1 oxygen atom. If you understand the rules of chemical bonding, then you can figure out what the structure of this molecule would actually look like. So just take a quick moment to analyze here. Hydrogen can only make 1 bond, which means if I have an element and it's connected to hydrogen, I can't have anything connected to the other side of that hydrogen, because that would mean that we have 2 bonds to hydrogen, so that can't work. So hydrogen always has to kind of go around the outside of molecules. It can go on the terminal end, it can go right at be the last thing on there, or it can be attached to something in the center, but it can't be bridging to other atoms. So that means that either we have carbon attached to oxygen, or we have oxygen attached to carbon, and these two are equivalent. This is the same thing, just flipped around backwards. So both of these will be fine. I'll use this one here on the left as my sample. So we know that we have carbon and oxygen. We have those accounted for. Where do the hydrogens go? Well, we have all of these bonds left over. 2 bonds to oxygen, right? So it's already bound once to the carbon. The other bond must be to one of these hydrogens. So we got 1 of the 4 hydrogens accounted for. 4 bonds to carbon, 1 bond is being taken up by oxygen. So the other 3 bonds to carbon must be hydrogen. And this is a substance called methyl alcohol. Methyl alcohol is wood alcohol. This is the stuff that if you drink it, you will probably go blind. Now, typically, you wouldn't actually see it written quite like this. It would probably be written like this. To give you a little bit more help, they would say something like CH3OH. We're going to talk about functional groups later on, but this is a hydroxyl group. And when you see that, you know that you're dealing with an alcohol. Just a hydrocarbon with a hydroxyl attached to it, that makes it an alcohol. Now, if I want to get a little bit more complicated, so let's go on to my next molecule here. What if I had the molecular formula C2H6O? What would that molecule look like? Now, for methyl alcohol, there was only one way that you could construct a valid molecular setup, a valid structure to that molecule. But this one actually has 2 different options. So, again, hydrogens can't bridge 2 elements because they can only make 1 bond. They have to kind of be on the outside of the molecule. But oxygen can make 2 bonds and carbon can make 4. They could both be in the center. So what we know is that either this molecule has 2 carbons and an oxygen, or it has a carbon, an oxygen, and a carbon. Now, it could also have an oxygen followed by 2 carbons, but that would be the same as this one up here. So these are really the 2 possibilities that we have. Well, what if we put in the hydrogens just to fill both of these structures out? Oh, this has no additional bonds. hydrogen, 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 hydrogen. Okay, so down here we have 6 hydrogens. 1, 2, 3, 4, 5, 6. Up here we have 1, 2, 3, 4, 5, 6 hydrogens. So both of these would be valid structural formulas for a chemical compound with this molecular formula here. And these are actually 2 different chemicals here. So this one here, what do we have? A hydrocarbon with a hydroxyl group on the end. We just learned from the last example that that makes it an alcohol. And in fact, this is ethyl alcohol. So having 2 carbons is what we refer to as a ethyl group here, two carbons with nothing but hydrogens attached to them. So instead of methyl alcohol, it was ethyl alcohol. Here you can actually see that we have a carbon on either side, a CH3 and a CH3. CH3, if you have any time you have just a CH3 attached to something, we call that a methyl group. Probably one of the most common functional groups you guys are going to see in early biology problems. And we have 2 methyl groups attached to an oxygen. When you have 2 important groups attached via a oxygen like that, so it goes carbon, oxygen, carbon. But this makes it an ether, a type of chemical, and this one would be called, oops, my hand's getting away from me, dimethyl, because there's 2 methyl groups, ether. Okay. So both of these, dimethyl ether and ethyl alcohol, which is, by the way, the kind of stuff that you find in beer, wine, sometimes rubbing alcohol and that sort of thing, but gasoline, it's the same stuff we put into gasoline, along with a bunch of other compounds. You would get the exact same molecular formula, even though these have 2 different structural formulas. That happens in more complicated types of molecules as well. So for example, one chemical that you're going to need to know about has the chemical formula C6, 1, 2, 3, 4, 5, 6, H12O6. Now, I have 6 carbons and 6 oxygens. That tells me that probably every carbon has an oxygen. So let's alrighty. Now let's put some hydrogens around here. It's a very relaxing thing, trying to solve chemical formulas. A little trial and error involved. This one I happen to just kind of know, so that's why I'm not walking you through it, because there's many different ways you could put this together. And what I know is that there's actually a double bond to oxygen on this carbon right here, and this is glucose. And look at that, I've actually made a mistake here, I think. Or did I? Let's count up our hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh no, I'm good. I'm good. We got 6 carbons, 6 oxygens, and 12 hydrogens. Now, there's another way that this molecule could have been put together. I could have, instead, one, 2, 3, 4, 5, 6. What if instead I put the double bond to oxygen on this carbon here? What would that give me up here? I would still have an OH, and everything else is just going to get an OH. Okay, so now I have 1, 2, 3, 4, 5, 6 oxygens as well. Fill out everything else with a hydrogen. So this would actually get an H2. You get, there's going to be 2 hydrogens attached to that one. But this one will have an H, an H, an H, and this one would have an H2 as well. So, let's see here. Let me just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Where have I made a mistake? Ah! 4 bonds to carbon. I had 5 because we have 1 to this carbon, 1 to this carbon, and 2 to this oxygen. Okay, so there wouldn't be any extra bond to that one, and now we have our 12 C6 H12O6, and this chemical structure is fructose. When you have this, like dimethyl ether and ethanol, or like glucose and fructose, where they have the exact same molecular formula, but different structural formulas, we say that they are isomers. Okay? So, if you know a little bit about the bonding, it makes it easier to figure out what the structure of molecules are, but you sometimes do need to know just a little bit more in order to figure out which structure is the correct structure, because there could be multiple correct answers. Now, here's one for you guys to try out. This one's going to be pretty easy, but it's for you guys to get some practice in. Pause the video. I have a common molecule that we are going to talk about, CO2. What do you think a CO2 molecule looks like? Write out the structural formula for CO2. Pause the video and then give it a shot. Okay. So we have a carbon and some oxygen. No hydrogens in here, so something's weird is going on, because a lot of the molecules we've looked at, they had hydrogens all around the outside, but this only has so many possibilities here because we have no hydrogens. So we could either have it arranged like this with the carbon on one side, we could flip it around the other way as well, but that would be the same thing, or we could have the carbon in the center. So these are 2 possibilities. So let's try this top one. If carbon is attached to oxygen and oxygen to the other oxygen, well, this oxygen here has already fulfilled all of its bonds. This oxygen is missing a bond, right? It should have 2, but it's only got the 1 right now. And this carbon is actually missing 3 bonds over here. So this won't work. That's not going to function as a structural formula. So if we take a look down here, what's going to happen? Well, each of these oxygens could bond with a double bond to this carbon, and if they do that, both oxygens have 2 bonds, and the carbon has 4 bonds. So CO2 looks like this. It's a linear molecule with 2 sets of double bonds. So let's bring in my snatoms for a moment, right? We had 2 oxygen atoms, right? We knew CO2, and we had a carbon atom. And in order to fill out their bond structure, we decided to use double bonds, like that. Oops. Like that. So this would be a carbon dioxide molecule. And you'll see carbon dioxides come up a lot in this class because they're involved in respiration, right? You breathe in oxygen, O2, and you breathe out carbon dioxide. So they're involved in your own metabolism. And they're also involved in photosynthesis, because we need to take these carbon dioxide molecules in order to make glucose and fructose. We take carbon dioxide and water and we rearrange them to make glucose in photosynthesis. So it's probably good that you see what it looks like right now. What about some of these other structures, right? We looked at a bunch of things. So how about ethyl alcohol? Everyone likes ethyl alcohol. Well, I mean, I don't, because it makes me sick, but most people seem to like it just fine. Alright, so we have our 2 carbons and our oxygen here. What's missing? We don't have any hydrogens. 1 bond for every hydrogen. So each hydrogen just kind of goes around the outside like it's decorating it, like it's adorning it with ping pong balls. Right? Alright, and that's ethyl alcohol. CH3, CH2, OH is the way that the formula is usually written. So CH3, CH2, OH. That's ethyl alcohol. And one thing that has always struck me about this molecule is how much it looks like a little puppy dog, like a little poodle dog here with the little ball of the tail, and here's the snout, and here's the oxygen head. So if you remember nothing else from this video lecture, here's wagging his tail, remember that ethyl alcohol looks like a puppy. Now the reason why I want to make sure that you guys have an understanding of what some simple molecules look like and you get a handle on how these bonds work is because it's going to get a little bit more complicated in a moment. So this is an amino acid right here. I know it's an amino acid because of a couple things. One, this is nitrogen attached to 2 hydrogens. NH2, that's called an amino group. And that's on one side. So amino acids have an amino group. Okay, so I can identify it already. The amino group's attached to a central carbon with a hydrogen. And then it's got this, a COOH group, a C double bonded to one oxygen, single bonded to another oxygen with a hydrogen on it. This is called a carboxyl group, but it's also an acid group. This makes it an acid. So an amino acid has an amino group and an acid group attached to it. And then we have 20 different kinds of amino acids. So we have always one hydrogen attached to the center carbon, but something else can be attached here. This amino acid is glycine. It's the simplest one, so I just have an extra hydrogen attached to it. But here I have, oh dear, I have cysteine, which is a slightly more complex amino acid. It still has all the same groups though. Here, I'll show you. We got our amino group, our acid group, there, that way it's the same way it was before, and then we have our central carbon with a hydrogen. It's just that we add another carbon with a sulfur group attached to it on here, and that's cysteine. So being able to analyze how molecules come together and what the common arrangements are of certain groups and atoms is going to be pretty useful in being able to understand how, say, amino acids work or DNA or any of this kind of thing.